Alright, here I'm going to go through an example of putting capacitors in series and parallel. First, we're going to start with a circuit with a 12-volt battery attached to three different capacitors. Capacitor 1, 2, and 3. Now in this case, looking at this, what we want to be able to do is identify that this is a series circuit. And the way that I know that is if I follow from my battery, the path of an electron is going to be through the wire and to this first capacitor. And now it hits a wall. And as electrons pile up here, what they're going to do is they're going to encourage electrons on this side, through the repulsion of the forces from like charges, to leave that capacitor and pile up on the next one, which encourages electrons to pile up on the next one, and then finally back to the battery. In this way, if you were just tracing a line across this entire circuit, you wouldn't be able to get back to the battery without going through multiple capacitors, which tells you that at least some of them, and in this case all three, are in series. In the case of parallel, we'll see that that's not the case. So let me finish putting in some information here. So we have three different capacitors. I'll call this one capacitor 1, and it has a capacitance of 4 farads. We'll call this capacitor 2. It has 12 farads of capacitance. And capacitor 3, which we'll say has 15 farads of capacitance. Now what I'd like to do with this circuit is solve for the charge on this capacitor. I'd like to know the voltage on that one as well. I'd like to know the charge and voltage here for the second one. And same thing for the third one. So I want to kind of get all the information about what's going on with these three capacitors if I hook this up to a 12-volt battery. Now the problem is that I have an equation. It's a great equation. It says that capacitance is equal to charge divided by voltage, which tells me how many coulombs charge per volt strength of the battery that I attach to this, that the capacitor can handle. Basically, a larger capacitance means you can pile more coulombs of charge onto those plates for each volt that you attach it to. If you want more charge, put a bigger battery. The problem, though, is that I only have one C value, and yet I have three separate C values here. Now, the quick thing that you might jump to is saying, well, I just plug in 12 here, and I plug in my three different C's, and I get three different Q values. And that would be okay, except that the voltage across each one of these isn't going to be 12. And the way that I know that is because, as we recall, when we look at the voltage of a battery, that's the difference from the negative terminal to the positive terminal, which means that if I add up all the voltages following a loop around this circuit, I should get 12. If each one was 12, I'm going to get 36. Something's wrong with my circuit. So really, the solution comes from I have to consolidate this circuit, and I do that by combining capacitors. So when we have capacitors in series, what we do is first off, I'm going to draw a little arrow, and I'm going to make a note for myself that these are in series. And I'm going to redraw this now with one consolidated capacitor. And to figure out what the capacitance value of that capacitor is, what I need to do is take the equation for a series circuit for the equivalent capacitance. And that equation is 1 over quantity 1 over C1 plus 1 over C2 plus 1 over C3. And when I plug in my C1, C2, and C3 values, I get 4 farads for C1, 12 farads for C2, and 15 for C3. You just have to be careful with parentheses around this. Depending on how your calculator works and how you type this in, it's easy to make a mistake with order of operations getting all kinds of messed up from this. So just be careful with that. In any case, when I plug that in, I get a value of 2.5. So again, what I do is 1 over 4 plus 1 over 12 plus 1 over 15, and I get 2.5. 2.5 farads. So my capacitance then down here is 2.5 farads, and what that means is that if I removed all three of these capacitors, I could replace them with one 2.5 farad capacitor, and functionally it would be a very similar circuit. Now, why did I do that? Well, now we go back to the equation that says C equals Q over V. Now I have one C value, I have one voltage, and so what I can do is I can fill in then all of my values for this combined capacitor because I know it's 12 volts. Looking across the sides of this capacitor, it's the same as across the sides of the battery, and therefore the total voltage difference is 12 volts. And so to find Q, I just rearrange this equation up here and I say, well, Q then is equal to C times phi. So 12 times 2.5 gives me 30. And my unit here is coulombs because it's charge, so 30 coulombs. All right, not done yet. Unfortunately, there's one more step, and what I need to do here is get back to my original answer, because what I wanted to do was find the charge and voltage for each of these three capacitors. Now what I can do though is I can bring back some of this information with me. And so that's when I go back here to my arrow and I remind myself that what I did here was I combined three capacitors that were in series. And when capacitors are in series, as we previously learned, they have the same charge. And the reason for that is because electrons that leave this terminal of the battery pile up on this capacitor, and the same number of electrons are going to get pushed away from this side and pile up on this capacitor, and the same number of electrons will pile up on this one, and then the same number will return to the battery. And so in the end, all three will have the same charge. And what that means is that I can take my 30 coulombs here and I can apply it actually to all three of my capacitors, because all three will get 30 coulombs worth of charge. And now it's just a matter of doing some math to solve for my voltages. And voltage is equal to Q charge divided by C. 30 divided by 15 gives me 2 volts. 30 divided by 12, let's do some heavy math here, gives me 2.5. And the last one, 30 divided by 4, gives me 7.5 volts. Just one last step to double check that I have done this correctly. As you recall, going one complete loop around a circuit will always add up to 12 volts, so I can check that. I have 2 volts here as I get to this capacitor, plus 2.5 volts, so right now we're at a total of 4.5, and add to that the 7.5 from this third capacitor, and we're back to the 12. So there we go. A bit of work, but that is capacitors in series. What I'd like to look at now is what happens when we have capacitors in parallel. So I'm going to draw my battery here. We'll call this a 6-volt battery. And it's going to be hooked up to 3 different capacitors in parallel. So my first capacitor, my second capacitor, and I want to give myself a good amount of room. My third capacitor, I need to fix my lines a little bit here. And back to the battery. The first one here, we'll call it C1. It has a capacitance of 2 farads. Sorry, it's a little bit small. Q1 and V1, because I'm going to want to find the charge and voltage on each of these. I'm just going to draw a line up here. C2 is 8 farads capacitance. We'll find Q2 and we'll find V2. And then C3 is 4 farads. Q3 and voltage 3. Okay. With this, I can combine them in much the same way that I did for the series capacitors. And by that, I mean that I can draw my arrow, I can write that I'm going to combine these in parallel, and I can recreate the circuit 6 volts with just one combined capacitor. When I do that, it's a little bit of extra work than what we're going to need to do, as you're going to see in a second. But when we have parallel and we're finding the equivalent capacitance, what we find is that the equivalent capacitance is actually just the sum of the capacitance values for the other 3. So I get 2, 8, and 4. So the equation is C1 plus C2 plus C3. In this example, not very hard math. 2 plus 8 plus 4 gives me 14 farads. So I have a capacitance of 14 farads down here. Now my voltage is going to be the 6 volts, because again, my voltage here is just the difference across the battery, and when I look at this, the difference across this capacitor is going to be the same thing. It's the same as making the jump across the battery. And so I say that my voltage is 6 volts. So 6 times 14 should give me my charge. So that gives me 60, about 84, if I did my math right there. So 84 coulombs of charge. Now, just like before, I don't have my final answer here yet, but what I can do is I can bring back some of this information to the previous diagram. And in the case of parallel, what we find is that instead of charge being the same, it's actually voltage that's the same in a parallel circuit. And so I bring back my 6 volts. Now, the reason why I had said before that this is a little bit more work than what we needed to do is because as soon as we see that this is parallel, we should have known that it's 6 volts for all of them. And the reason for that is if you follow any one pathway around this diagram, you get to this junction and you can make one of 3 choices. And the point is, it doesn't really matter which choice you make. When you make the jump over one of these capacitors, you're going to have gone through a total of 6 volts. Because in either case, whether you go left, up the middle, or to the right, you only have to go over one device in order to be now on the other side of the battery. And so each one must have a potential difference or voltage of 6 volts. Now that I have the voltage of 6 volts for each of these, I can go ahead and I can find my Q values. Again, just reminding ourselves, C equals Q over V. To find my charge, what I need to do is Q equals C times V. So in this case, it's 6 times 4, which gives me 24 coulombs. In this case, 6 times 8, 48 coulombs. And over here in Q1, it's 6 times 2, so 12 coulombs. Just like in the previous example, I can check my work here to make sure that I've done this correctly. And I do so by checking that the total charge that's stored up by these 3 capacitors here is the same as when I had one equivalent capacitor. So basically the sum of these 3 charges should equal 84 coulombs. And when I check it, 12 plus 48 gives me 60, 60 plus 24 gives me 84 coulombs. And there we go. So in the end, I do in fact have 84 coulombs stored across these 3, so I can be relatively confident that my numbers are correct and that I haven't made any math errors in this. So that's combining capacitors in parallel.